Let's introduce the natural logarithm. It's based on the natural exponential function. So recall, the natural exponential function is the function f of x equaling e to the x power, where e is the magic number that begins with 2.71828 and so on. The graph of the natural exponential function grows exceedingly rapidly. So if I sketch the graph, it might look something like this. It starts off on the left, very, very close to the x-axis, almost imperceptibly close, and then shoots up extremely quickly after it crosses the y-axis. So it passes through 1 here and moves like this. So very, very close to the x-axis. I'm not even doing it justice with this gap you see here, and then shoots up very, very quickly. There is the graph of e to the x. So if you notice the graph, this function passes the horizontal line test. Maybe it doesn't look like that in my drawing because it maybe appears that this part of the graph is almost horizontal, but it's very, very slightly slanted up. So this function indeed passes the horizontal line test, meaning this function is 1-to-1, and meaning this function has an inverse. So what we do is we let ln x, and this is pronounced log x, be the inverse to e to the x. So log x is the natural logarithm. Log x is defined to be the inverse to e to the x. And you can graph the inverse by reflecting about the line y equals x. So if this is the diagonal line, y equals x, you could flip the graph over and find the graph of log x. So let me draw the graph of log x. If I reflect about the line y equals x, it's going to pass through this value here and go something like this. So that's the graph of log x, natural log x. Let me write down some properties of log x that we can get right away from this definition. So here are properties. So property 1 is the domain of the natural log x is all numbers that are positive. You can't plug in a negative number here. That's not in the domain of the function. The domain of the function is everything from 0 to infinity. The range, however, the range of natural log is all real numbers, anything from negative infinity to infinity. You have a vertical asymptote here at 0, so this function comes up, it hits all values until you get to the x-axis, and then it actually grows quite slowly, but always getting bigger, and has limit over here to the right as big of a number as you choose. So the range is negative infinity to infinity. It's pretty clear from the graph that the natural log x is always increasing. It's going up, it's never going down. Another property that you can get right away from the picture is log of 1. If I plug in 1 here, I get out 0. So the only 0 of the logarithm function, log x, is at x equals 1. And then lastly, I'm going to just write down this property that comes straight from what we define it to be. Log x is the inverse to e to the x. What that means is, if you compose these two functions, putting one inside the other, they cancel each other out. So log e to the x is just x, and if you compose them in the reverse order, e to the log x power, you again just get x. So this is what it means to be an inverse. Let's do an example here. what if I said to find the domain, so what is the domain of log 1 plus x divided by 1 minus x? Well, if you look at this definition, the domain of regular old ln x is 0 to infinity, meaning you can only take a log of a positive number. So log of -1 is garbage. You can only put in positive numbers inside of the logarithm function. So that means the domain is whatever x values I can plug in to make this input into the logarithm function positive. So we need 1 plus x over 1 minus x to be positive. You can't even plug in 0 to log x. You can get out 0, but you can't plug in 0 to log x. The way that we solve rational inequalities is by plotting the zeros and the vertical asymptotes on a number line. So there's a 0 at -1, and there's a vertical asymptote at x equals 1. This divvies the line into regions, and I could test the values of this function on each region. If I plug in a value less than -1, I'll get a negative. On this region, in between -1 and 1, I get a positive, and over here, negative. So the domain is the positive numbers, and those are the values in between -1 and 1. Let's finish this video with one more example, playing with our new toy, the logarithm function. Let's plot log 2 plus x minus 1. So I know the graph of log x looks like this. The graph of the function I'm trying to plot is similar, but just shifted. What this means is I'm going to shift the graph to the left by 2 and up by 1. So I'm going to shift up by 2, excuse me, up by 1. Actually, it's up by -1. This is the up or down vertical shift, and the horizontal shift is inside the argument. So I'm going to shift up by -1, and I'm going to shift left by 2. Let's see what that would be. So I'm going to take my picture, and instead of having a vertical asymptote at 0, I believe that vertical asymptote is going to be at -2. So I have this vertical asymptote here at -2, and I'm shifting the whole picture down by 1. So I believe this value where it crosses the x-axis will be transformed into a value here at -1. Therefore, the picture is going to look something like this. I don't think it crosses through the origin. My picture made it look like that. I think it goes a little bit past, but there is an approximate picture of the graph of this function. Okay, wonderful.